Lecture of the semester. Today I will speak about watch literals, a technique to propagate efficiently logical constraints. Then I will discuss about modeling, because modeling is really an art in constraint programming, and I will discuss about the bin packing constraint. Then I will discuss about the symmetry problem when we explore large subspace and how we can avoid it and limit the problem of symmetries. Let's start with the watch literal techniques. So the constraint that we are interested in is this constraint. It's a OR constraint between Boolean variables. So every variable that you see here is a Boolean variable. Okay, so it can take the value 0 for false or 1 for true. And the goal of this constraint is that at least one of these values, one of these variables takes the value 1. Okay, so one of them must be 1. So if all of them are 0 everywhere, then the constraint is not satisfied. If at least one of them is 1, then it's okay. Okay, the constraint is satisfied. And think about this constraint a little bit, and you will realize that you can only propagate when all the variables are false, except 1. Okay? If all the variables are false except 1, then you can do something that we call unit propagation. So let's look at one example. Assume that I have 3 variables. So one of them is still 0, 1, 0, 1, and this one is 1, let's say. You cannot really do anything about these 2 variables, right? You cannot do anything. But if all of them are fixed and they are 0, then you can do something, okay? If all of them are false, so if you have 0, 0, and then 0, 1, you already know that because all these 2 variables are already 0, you know that this one is forbidden to take the value 0, because otherwise the OR will not be satisfied. So the OR constraint can be formulated like this as well. So it can be formulated like the sum of the xi should be larger or equal to 1. Okay, this is completely equivalent to this arithmetic constraint if you assume that 0 is for false and 1 is for true. This kind of propagation that we call the unit propagation for the OR constraint is the only propagation that is used by SAT solvers. Okay. Let's think about the first implementation that we could do. You can listen to all the variables, and then you will maintain a sparse set with the bound and unbound variables. If one variable becomes true, you will deactivate the constraint because it is satisfied, and so there is nothing else to do. You know that it will remain satisfied, whatever the other variable takes. If the sparse set becomes empty, then all the variables are false, and you can throw an inconsistency exception. But if only one variable is unbound and the other ones are false, then you can do the unit propagation and force the last one to become true. This is just what we did before. All of this can be done in constant time per variable change. But can we do better than this constant time per variable change? Which means basically order of 0, so do nothing. And the answer is yes, we can do even better than this. The idea is the following, is we will not listen, this is a key idea, we will not listen to all the variables. Okay, we will not listen to all the changes. We will only be listening to 2 variables in the set of n variables. And the 2 variables that we will listen to are the unbound variables that is to the left, and the leftmost unbound variables and the rightmost unbound variables. So this is the leftmost unbound variables, and this is the rightmost unbound variable in our vector. Okay, and so we will move like this. You know that an invariant will be that the other one are already fixed to 0, and so at this specific time we will only be listening to x3 and x7. The rest we don't listen to them. So if x4 changes, we don't care. Okay, we will only be listening to these 2 variables. And why only 2? Because we know that if 2 variables are unbound, the constraint can still be satisfied. And so we don't really care if x4 becomes a 0 or a 1. We don't care about this, okay? We are only interested to do the unit propagation, and the unit propagation can only occur when all the variables but 1 is unbound, okay? All the variables are bound except 1, okay? So if the 2 variables that we are listening to are not yet bound, we know that we cannot really do the unit propagation, okay? So that's the idea. And so to listen to the changes on x3 and x7, we will do that with propagate on bind and propagate on bind on x7, okay? So this is the leftmost unbound and this is the rightmost unbound. So as I said, if this one suddenly becomes bound, we don't care. We cannot do anything. We can do the unit propagation because x3 and x7 are still not bound. Okay. If x7 becomes bound, then you simply move the pointer and you now start to listen to x6 instead of x7, which is now bound. Okay. So at any point in time, you are only listening to two variables. Okay. These are the possible cases that might occur when we update the leftmost index and the rightmost index. Is first, if you realize that the two pointers are pointing to the same variables, it basically means that you are listening to the last unbound variables and all the other ones are 0, okay? You are listening here to a 0, 1 variables and all the other one has been set to 0, okay? And this is the situation in which you have W left is equal to WR, right? And so in that case, the last one, this one, because all the other ones are already set to 0, this one must be equal to 1, okay? That's the unit propagation case. Then the other case is WL exceeds WR. And so if this happens, it means that the vector is set to 0 everywhere and you must fail. You have an inconsistency. You were not able to satisfy that at least one variable should take the value 1. Okay. A slightly more difficult constraint is the reified OR. Okay, so B is set to true only if at least one variable among x1 to xn is true. Okay. And so you might propagate in that direction, but also in that direction. Okay. Assume B is set to true. So this is this situation. B is set to true, then you must post the OR constraint. Dynamically, you can post the OR constraint that we just studied before using the watch literals. If B is set to false, then you will set all the variables to false because the OR shouldn't be satisfied, which means that all of them are set to 0. Okay, let's study now the other direction, this one, okay? If one variable becomes true, let's say x2, if x2 becomes true, then you can safely set B to true, okay? So B is set to true because you know that the OR is satisfied. And if all the x1s to xn are set to false, okay, you know that the OR is not satisfied and you set B to false, okay? So there are 4 different cases for this constraint and one of them is dynamically posting the OR constraint that we just studied before.